Okay, greetings aspiring scientists. Welcome to my video today. I hope you're doing well. So today we're going to be finishing up the fuels section of SL chemistry. This will involve mostly biofuels and various fuel cells. So just continuing on from what I did in my previous video about combustion and greenhouse gases. So let's get into it. Go to my slides. We'll start with 1.3.4 on biofuels. So I've already talked a little bit in my previous videos about biofuels, actually. When we talked about combusting alcohols such as ethanol, those can be made from organisms that do photosynthesis, and we can take the glucose that they make and ferment it into CO2 and ethanol, which we can then combust. So, biofuels are a renewable fuel energy source which is produced by changing light energy from the sun into chemical potential energy in the form of organic molecules. Mainly, glucose is sort of the fundamental base unit, I think most biology people would say. Now, the most well-known is the Calvin cycle. This is a process used by plants in photosynthesis to produce glucose from water and carbon dioxide. So 6 CO2 gas molecules come in with 6 water molecules, H2O, to make 1 glucose, C6H12O6 plus 6 O2. Now, I think this is a very simplified or general equation for what happens, but there's a lot of little small steps and intermediates along the way to actually get glucose from 6 CO2 and water. So why don't we just combust glucose as our biofuel? Well, pure glucose is a non-volatile solid, like a sugary powder maybe, or crystal. It's not a great fuel for most purposes. Crystals like that don't combust particularly well. But it can be fermented to volatile liquid ethanol. We can get 2 ethanol molecules and 2 CO2 molecules out of a glucose, C6H12O6. And we also know glucose can be dissolved in water, like sugar water, aqueous. But in that case, if you try to combust it, all the heat you would put in kind of gets absorbed by the water solvent around it, so that also doesn't work. So we're better off trying to make our volatile liquid ethanol. Now, those of you who are interested, here's a little diagram of the Calvin cycle from this website I found. I thought it was pretty good. We do not need to know this in chemistry class, but it is pretty interesting. There's a lot of things going on, a lot of weird names and symbols. But what you can focus on is that 3 CO2 units come in the top here per 1 cycle, and a bunch of things will happen, but the output from this is down here at the bottom, 3 carbon chain, G3P. So sort of the net result of this Calvin cycle is 3 CO2 comes in, and then they get linked together, carbon-carbon bonded, in this G3P unit, which can then go on to make glucose, maybe if 2 of those combine together. But along the way, various things happen, right? Actually, within this cycle, we have longer chains going on. We have, in the first step here, like one of these CO2 atoms gets stuck on a 5 carbon chain to make a 6 carbon thing, and we'll do that 3 times to make 3 of those. But then some shifting around happens, and instead of 3 6-unit chains, we instead make 6 3-unit chains, but the number of carbons there should be basically the same. Some further transformations, ATP will come in. That's like a phosphorylating agent, which changes the energies and transition states of these chains. Then that can shift to our G3P. One of those can leave. If one leaves, we then get 5 G3P. That can rearrange. So 5 times 3 is 15, but we'll rearrange it to make 3 5 chains on the left 3 times 5 is also 15. Keep the numbers the same. And then the cycle will repeat. It'll try to get another CO2 unit to attach on to make our 6 carbon chain. So a lot of things going on there. There's carboxylic acids, aldehydes, various organic type molecules being oxidized and reduced throughout this process. We don't need to know that, but if you are interested, check out the Kelvin cycle. Based on everything we've learned in chemistry, you can understand a lot of what's going on here with structure, stability, transition states, conservation of energy and matter, I would hope. But yeah, the result of this is that glucose will be made from our G3P groups that come out the bottom here. 2 of those can come together to make glucose. Then we have fermentation. So I looked up what this means. It's really a process in which microorganisms in low oxygen environments break down large carbohydrates to form smaller acids, maybe like lactic acid, gases like CO2, or alcohols usually, like ethanol. Okay, so microorganisms can break down glucose, C6H12O6, in anaerobic environments. That means low or no oxygen. If there was oxygen, they'd probably just do regular like cellular respiration and make CO2 with it. But if there's not oxygen nearby, we can form 2 ethanol molecules and 2 carbon dioxide molecules. This will release the greenhouse gas CO2, which sounds bad, right? It's greenhouse gas, but realize that 6 CO2 molecules were taken out of the atmosphere to make glucose, as evidenced from the Kelvin cycle I showed here. To make glucose, we take 3 CO2 out of the atmosphere. Okay, so it's sort of like we're borrowing it for some chemical potential energy and then re-releasing it when we combust our ethanol, when we ferment our glucose as well. We're just returning some borrowed CO2. It's very different than combusting an alkane, which is a lot of carbon that's trapped underground, not part of the sort of weather systems going on, but we combust it and then release CO2, extra CO2 that wasn't in the weather system. So what are the advantages and disadvantages of ethanol biofuel? Well, advantages first, it's renewable. As long as we can make plants and bacteria and things that do photosynthesis, we can ferment and make ethanol and collect it. Just using sunlight, basically, power of the sun. There's a wide range of sources of biofuel. So anything that has glucose or does photosynthesis, there's various plants, animals, bacteria that do this. It is sustainable, so it's not like we're going to really run out of sunlight or living organisms. Reduce greenhouse gas emissions. So we can't say zero necessarily because CO2 is released, but there's sort of zero net emissions because we assume that all of the ethanol that we would maybe combust for fuel came from glucose and photosynthesis that took it out of the atmosphere first. And then finally, countries can be independent with regards to fuel production. So almost any country can have a way to get biofuel in theory, as long as they can farm a bit. But fossil fuels are sort of locked behind countries that have oil, right? Like Russia, Saudi Arabia, the USA, Canada have a lot of oil naturally in or around them. And that's very powerful for them and makes other countries struggle and have to, pay and buy fossil fuels from those larger countries. So if you could just harvest biofuel yourself, you can be more independent. That's an advantage. Disadvantages, though, there are certainly many. This requires many resources to farm. So you need to set up facilities and have the resources and food and proper sunlight, weather conditions to actually get these things growing and producing glucose and ethanol. Deforestation is a possible consequence. So, we can just go chop a bunch of plants down right now and ferment them into glucose or into ethanol, but do we really want to chop down that much vegetation and habitats and destroy the ecosystem? It's a valid question, and it's a disadvantage of just suddenly trying to make a lot of ethanol. Mass producing a single type of organism reduces biodiversity. This is kind of a biological concern, but oftentimes when we're trying to farm and harvest organisms to get this ethanol, we're going to sort of like choose the best one and even engineer it genetically to just produce the best glucose and ethanol possible, and then just take that DNA and make as many organisms of that type as possible. But that sort of defeats the process of biodiversity and evolution and survival, natural survival, which has consequences. Like it can be very weak to one certain disease type, for example, or it can overtake the weaker species and eliminate them, and those weaker species might be something that we needed for something else, or we just enjoy the biodiversity of those other species. Materials could often be used for food instead. This is a big concern. So we're getting ethanol from plants, and oftentimes the best sources are those with high glucose, maybe like, I don't know, corn or other grains or vegetables, and we could use those for food instead, right? We could feed people, and that's often the first concern rather than making fuels or environmentally friendly fuels. It's to feed people. So if we need to feed people, we probably can't do max ethanol production. Ethanol can be consumed by the human body for calories, I think, but it's very unhealthy to just have a main diet of alcohol, basically. Okay, so the cost of production is very high compared to fossil fuels, where we can, these days, pretty efficiently drill a hole and pull out tons and tons of cubic meters of fossil fuels cheaply. To actually grow and extract ethanol can be pretty expensive comparatively. So some practice. Write the balanced chemical equation for the fermentation of glucose. This will not be in your data book, but you need to memorize or come up with it yourself. So, start with your glucose. You should memorize this formula, I think. 6 carbons, 12 hydrogens, 6 oxygens. C6H12O6. Usually when this is fermented, we can say that it's aqueous. And this just goes in an anaerobic environment without oxygen to make 2CO2 and 2 ethanol, C2H5OH, liquid. Okay, so like this. It can be argued then, part B, that ethanol-based fuels have a lower carbon footprint than fossil-based fuels, even though they both release similar amounts of carbon dioxide being released. Outline this argument. So maybe I'll type this instead. I don't really want to write this with my pen. Okay, I'll write this in yellow. So ethanol-based fuels are generated from glucose fermentation. Glucose is generated from photosynthesis, things like the Calvin cycle, which removes 6 CO2 from the atmosphere. And that's per molecule of glucose produced. So even if ethanol is combusted, the net release, so the resulting release of CO2 is essentially zero. That's the argument. But if you're very critical of any operation, you don't just consider the chemical formula. You consider what is the true cost of setting up the whole process. So when you make the tools, when you create the farming zone, when you distribute the fuel, those can also have emissions, right? They might require fossil fuels and energy to do various parts. So I would always recommend you try to at least show that you're aware that what might seem like zero net emissions from a single chemical formula, it doesn't represent the whole picture of actually distributing the energy to the customer, the consumer. Okay. C, discuss the arguments for the advantages and disadvantages of biofuels. Doesn't say how many, but usually 2 and 2 is a good rule. 2 advantages, 2 disadvantages. Try to go with the most obvious ones. So for advantages, renewable is huge. We're not going to run out. That's on its own a very good reason to focus on such kind of fuels. What else is good about biofuels and ethanol? Reduced CO2 emissions. So we won't have as much greenhouse effects and disrupting our climate change. Not B, but disadvantages, we can say. What can we say? So the energy output per mole is less than most fossil fuels. So that's not great if we're trying to make the best fuel per mole. What else is not that great? Can disturb our food resources, especially in developing countries or countries that have food scarcity. Biofuels just might not be an option because we need those organisms for food instead. Okay, I think that's what I would say. All right, moving on. That's all for biofuels, so we'll move on to fuel cells, 1.3.5. Things can get fairly complicated in here. So, types of cells. When I say cells, this is something that you probably will understand as batteries. Batteries are often groups of cells put together to give us a certain required energy or voltage output. So we can have a primary or voltaic cell. This cell converts stored chemical potential energy into electrical energy. The reactions in the primary cells are usually irreversible, so the fuel kind of gets consumed and it becomes used when all the reactants have become products. So for example, a zinc manganese dioxide battery, you use it, get some energy output, and then when it's dead. All the reactants have become products. But there are secondary cells, but this cell contains chemicals which can undergo reversible reactions, and it is therefore rechargeable with electrical energy input. It lasts much longer because we can recharge it and reuse it, but it may still have a limited lifetime, a limited number of recharges or charging cycles. An example of this is the lead acid car battery. So in most cars, especially older style ones, maybe modern electric cars have something different, but standard lead acid car battery is used in a lot of cars and it recharges as you drive, but it's used for things like your headlights and starting the engine and such. And then there's fuel cells. So the cell in a fuel cell consumes a fuel to turn chemical energy into electrical energy. It will provide electrical energy as long as fuel is being supplied. For example, the hydrogen fuel cell uses H2 gas, hydrogen, as a fuel. So all of these have advantages and disadvantages, whether they can just be made and disposed of easily or recharged and used more renewably. Or fuel cells don't need to be charged at all, but they can be reused, but they consume a fuel, unlike kind of the other cells. All right, so we need to consider reduction and oxidation reactions, because to understand what's happening in the fuel cells we're going to look at, we have to know about this. And really this comes from a future topic, redox reactions in like Reactivity 3, near the end of the curriculum, but we're going to teach it a little bit here just so we can understand. So if we consider the reaction between sodium metal and chlorine gas, this is a redox, meaning reduction and oxidation, simultaneous reaction. The sodium atoms lose an electron, -1e. The chlorine atoms gain electrons, 1e. So we can normally write this reaction as 2Na solid plus a Cl2 gas molecule goes to 2 NaCl, 2 salt units. And if this happens with large amounts of these elements, we can build up a crystal, an ionic salt, as we learned in ionic bonding section. But it's possible to write separate equations for the oxidation of sodium and the reduction of chlorine. They're kind of separate, right? Sodium gives up its electron, 2Na goes to 2Na plus 2E, and chlorine accepts the electrons and becomes anions. Cl2 plus 2E goes to 2Cl minus. So top is oxidation, bottom is reduction. And what you should find is if you add these two equations together, just add all the reactants on the left and the products on the right, we get 2Na plus Cl2 goes to 2 NaCl. So just like adding equations with Hess's law and enthalpies, things that appear equally on the left and right side disappear. That's what happens with the electrons in these equations. 2e on the left, 2e on the right. So the net change of electrons between these is essentially zero, which is what we expect, conservation of electrons there. So these two equations, the oxidation and reduction, are called half equations, because they represent each half of this redox reaction. When you add them together, they give you the whole equation. So there are some rules for how to go about finding these half equations. First, you kind of have to find out what is oxidized and reduced. So to do that, you need to consider the oxidation states of all atoms in your whole equation. So find the oxidation states of any atoms that can be found, then identify which species is reduced, which is oxidized through the process. Reduction will be getting more negative, oxidation will be getting more positive. So identify those and identify where the electrons must be going. They go from the thing that is oxidized to the thing that is reduced. Okay, third, balance the reduced and oxidized atoms in their half equations. Should do that. And 4 and 5 sort of go together with this. For the oxidation reaction, write the electrons lost on the right side and make sure that the atom which is losing it has an appropriately raised oxidation state. So if you go like iron 0 to iron 3 plus, that would be losing 3 electrons. So make sure all those numbers work out. 5 then, for the reduction reaction, write the electrons gained on the left side of your half equation, and the atom on the right side must have an appropriately lowered oxidation state. Make sure all the math works out. Now, step 6 is important. If you just need half equations, you actually don't really need to do 6 and 7, but 6 and 7 are sort of confirmations that you've got it right. So multiply one or both half equations so that the number of electrons lost in oxidation equals those gained in reduction. This really represents what will be happening in reality, because the electrons need to cancel out and be balanced. So, for example, if your top equation has an oxidation of 1 electron and your bottom equation has a reduction happening with 2 electrons, you know that the top oxidation equation must be happening twice to give those 2 electrons to the reduced species. We'll show some examples of that soon, but step 7 is just try adding both equations together. You should find the electrons all cancel because you should have equal numbers on the left and right. And then you should be left with your balanced whole chemical equation that makes sense. Sometimes this will be given in a question, sometimes not, but it's good to check. Okay, so we'll look at some very complicated questions to do with this later in Reactivity 3, but for now we're just going to look at the most simple types because like the hydrogen fuel cell is not that complicated. We don't need to get deep into this yet. So practice, write the half equations for the following redox reactions. Zinc solid plus copper 2 plus aqueous goes to zinc 2 plus aqueous plus copper solid. Quite easy if you know what you're doing. So, oxidation states, any pure element has oxidation state of 0. So what's gaining electrons, what's losing it? Well, it must be true that zinc is losing it if it's going 0 to 2 plus. So we'll do oxidation first. This will be zinc solid goes to 2 electrons, 2 E minus, and zinc aqueous, zinc 2 plus aqueous, and then reduction. So this must be copper 2 plus aqueous getting some electrons to go to copper 0, plus 2E goes to copper 0 solid. You don't have to write that 0 if you don't want. In fact, I probably shouldn't because I didn't write it for zinc. All right, so that's our oxidation and reduction half equations. And you can see that if I added these 2 together, I would get exactly the equation I have at the top for number 1. Zinc plus copper 2 plus goes to zinc 2 plus and copper 0. 2 electrons on the left, 2 electrons on the right, cancel out. So that's done. That's good. Number 2 then, Cl2 plus 2 Br minus goes to 2 Cl minus and Br2. So again, oxidation states of pure elements is 0. Oxidation states of these anions is -1. So we'll do oxidation. Should be the bromine does oxidation. 2 Br minus goes to Br2. Liquid, I believe, is its standard state. These we can say are aqueous. Plus 2E. And then reduction. We'll have the Cl2 gas get 2 electrons and go to 2 Cl minus aqueous. Okay, so we were lucky with these 2. They're very easy. We didn't have to multiply any of these. But you can imagine if there was a different number of electrons for oxidation versus reduction, you have to multiply either the top or the bottom or both to get some common whole number of electrons being transferred for this to make sense with conservation of matter and particles and charge. But for what we're doing today, this is probably good enough practice. So, hydrogen fuel cell, here we go. This is what it might look like, very basic kind of visual representation, and made with Claude AI. There are good, maybe better representations in textbooks that you can have. I use Oxford Course Companion. It's decently good diagrams. So the overall reaction of the hydrogen fuel cell is just the combustion of hydrogen. 2H2 plus O2 goes to H2O. But our goal here is to, we can check what the enthalpy of combustion would be for hydrogen and oxygen. It's fairly exothermic. But what happens when we just combust hydrogen with oxygen in the air is an explosion, right? A release of heat and pressure and sound and vibrations. We can't really take advantage of such an explosion, an uncontrolled thing. What we want is to take all that energy, all those joules, and get them as electrical energy. We can then, power a light bulb or a heater or something with our circuit here. This is what the load is. It's kind of like, can be a light bulb, maybe, imagine. So we're trying to get all that combustion energy, get it in the moving electrons and take advantage of it that way, so none of it's wasted as heat or sound or anything else. So the way to do that is to separate this reaction into half equations and half cells. So we're going to have, at the anode, H2 gas goes in. Goes in here, and it will be oxidized. So electrons flow out the top here and into our circuit, into our load. And that leaves us with H plus, right? So H plus has lost its electron. It goes in the center here, in the proton exchange membrane, PEM. This will be the electrolyte. And it's a very specially engineered and designed piece of this cell that only allows H plus to pass through from left to right. How it does that, I'm not exactly sure, but I'm pretty sure it has very small pores, like little holes, that only allow proton-sized things through. And it maybe has, a slight negative charge to sort of block any neutral or negative things from going through, and it allows our little positively charged protons to go through from left to right only. And that's important for what will happen later. But it turns out we cannot get 100% efficiency at this anode, so some of this H2 gas that couldn't get oxidized will just be pushed out as excess H2, but maybe we can just recirculate this and try again. Probably depends on the cell engineering. But we try to oxidize as much as possible. This anode will usually be a special piece of metal, conducting metal, like platinum maybe, to try to get the best efficiency out of this. And you can see the half equation there is written in the bottom left. H2 goes to 2H plus and 2 electrons. Okay, then what happens at the cathode? Another piece of metal catalyst electrode. Here we have O2 coming in, and it's going to pick up H plus, and it's also going to pick up a bunch of electrons. The electrons come in from the circuit. They come in from the anode, basically. When our hydrogen loses them, we can bring them into the cathode after they go through the circuit and change their energy level. So oxygen in with electrons, and what comes out then is H2O. So we just need oxygen from the air coming in, and we'll get some water vapor exhaust out. But there's no CO2 or any other exhaust products really. So this is very environmentally friendly, just breathing out water basically. And then our half equation for the cathode on the right is this. 1/2 O2 plus 2H plus 2E goes to H2O. And you should find if you add these two equations together, left side plus right side, you will get the equation at the top here. 2H2 plus O2 goes to 2H2O. But everything needs to be multiplied by 2 for that to actually work out. If we don't want any half numbers, like 1/2 O2, just multiply everything by 2. just multiply everything by 2. We'll get 2H2, 1 mole of O2 makes 2H2O. Okay, it looks a little bit complicated, but it's really not. The questions involved in this usually ask about what goes in, what goes out on each side, what does the proton exchange membrane do, why is it special, what are the directions of the electron flow maybe. In this case, with the anode on the left and cathode on the right, it is like clockwise around the circuit. So I do recommend you study this enough. All right, moving on. Summary of this, most of what I just said. So the proton exchange membrane, PEM, selectively allows only protons to pass through diffusion, but does not allow other ions, molecules, or electrons. How? Well, very small neutral or negative partially charged holes or pores will allow the protons to go through. Hydrogen gas is oxidized at the anode on the surface of a platinum-based metal catalyst. That equation is 2H2 goes to 4H plus 4E, multiplied by 2 for this to work out. And we should notice that electrons cannot pass through the proton exchange membrane, so they're forced out of the electrode as they start to build up through the external circuit, the wire that we connect to the top, into our load, the motor or the light bulb or the heating filament, whatever. And then protons formed at the anode flow across the PEM to the cathode. They are then combined with the incoming electrons and oxygen from the air to form water. That equation is O2 plus 4E goes plus 4H plus goes to 2H2O. Okay, and then a quick diagram here just to show what happens on each side and how they both use the H plus. One of them releases it into the PEM and the other one accepts it on the right side of the PEM. But the net result of this is basically just the combustion of hydrogen equation. But we control all this energy very carefully in the electric circuit. Okay. So the big issue with this is this requires hydrogen fuel. Where do we get hydrogen fuel? You don't just walk around and find it around Earth for several reasons. First of all, it's very reactive, so anytime there's heat or oxygen or whatever, it's likely to just combust into water. Second reason, though, is it's so light. It floats to the top of the atmosphere, and it can actually then just leave Earth. You might have heard this about helium as well. It's so light that it gets its escape velocity, okay? It can get enough speed to just leave Earth's gravity and go out into space. So that's what's happened to the hydrogen on Earth. It's either chemically reacted, mostly to water or some other minerals, or it's left due to its light weight and ability to get high speeds. So we can produce H2 gas from water using substantial energy input in a process called electrolysis. But we don't want to just hook up like a power plant or a huge battery to do hydrolysis, right? Because we're trying to make an efficient, renewable fuel here. So using a lot of fossil fuel energy for this sort of defeats the purpose of the hydrogen fuel cell. But there are ways to do it. It can be done through like solar panels, photovoltaic cells, they're called. Mostly like the solar panels you might see on some buildings or on the sides of the roads or in some facilities. But this is fairly slow and inefficient. There's a diagram I have on the right here. So if we have some acidic solution connected to our photovoltaic cell, we can do electrolysis and produce O2 gas on one side, H2 gas on the other, collect the H2, and then use it in our hydrogen fuel cell. This is not really economically viable on large scales yet, but maybe one of you can produce a better, more efficient system, and we can get hydrogen more in a more eco-friendly way. And so this is often overshadowed by the following method that I have on the following slide. So the main way I think that we do get it is through something called steam reforming. Now, hydrocarbons from fossil fuels can undergo a reaction with water in low oxygen environments to form hydrogen and carbon monoxide. So your fuel plus water in the form of steam, that's why it's called steam reforming, goes to carbon monoxide, CO, and H2. So this is not combustion. It's like another kind of anaerobic, low oxygen environment rearrangement of these atoms into CO and H2. And we can also have CO itself do another reaction with water to make CO2 and H2. So it's kind of very effective for producing a lot of hydrogen. But what's the problem with this? Look at all the CO2 that it's going to release. So as I mentioned, carbon monoxide can further react with water to make more hydrogen and CO2. Our general equations for this are underneath here on the right. We can produce a lot of moles of H2, but also a lot of moles of CO2. Essentially, every carbon that was in the hydrocarbon becomes a CO2 molecule. So this process is widely used to produce hydrogen H2 gas, but it releases significant amounts of CO2 to the environment. So if our goal with the hydrogen cell was to reduce greenhouse gas emissions, then we fail if we get our hydrogen fuel through steam reforming. So not in a good place at the moment if this is our main method, but this is why chemists and chemistry research is very important. We want to figure out if there's easier ways to get hydrogen, because there is a lot of it on Earth. It's just locked in things like water and hydrocarbons. All right, another thing we must consider is the direct methanol fuel cell, DMFC. The direct methanol fuel cell utilizes methanol instead of hydrogen gas to produce H+ ions, but otherwise it's very similar. There'll be CO2 and water involved as well. Methanol is renewable. It can be produced via fermentation of photosynthesized materials. So I mostly showed ethanol in the fermentation process, but certain bacteria or starting organic molecules can be fermented into methanol as well, 1-carbon alcohols. Now, although the DMFC produces CO2 and the hydrogen fuel cell does not, the production of H2 gas fuel itself through steam reforming causes more net CO2 release than the DMFC. The DMFC will use methanol from photosynthesis, which was taken from CO2 in the atmosphere, whereas steam reforming will release CO2 that was locked underneath the earth in fossil fuels. So if our goal is to reduce greenhouse gas emissions, the DMFC might actually be a better choice. It probably is at this point in time. Now, methanol also has far greater energy density, energy per unit volume, so like joules per meter cubed of fuel, than hydrogen. Now, we do need to consider the half equations. So the overall equation you can look at first, the kind of green on the bottom. It's just the combustion of methanol. This will have its own enthalpy. We make CO2 and water, but we don't want that explosion happening, right? The fire. We want to instead capture it in a cell, fuel cell, as electrical energy efficiently. So we split it into these two half equations. Methanol plus water goes to CO2 and H+ and electrons. That's the oxidation at the anode. Then the reduction will be reducing oxygen and O2 gas. So we take our O2 gas plus H+ and a bunch of electrons, we make water. If you add those together, we should get the net overall equation underneath, the combustion of methanol. So you can see this reaction does produce some CO2, 1 mole of CO2 per mole of methanol. But again, this is generally offset by photosynthesis. All of the methanol carbon came from the atmosphere to begin with. We're just borrowing it for our fuel, and then we re-release it. This reaction does require expensive and rare metal catalysts, though, such as ruthenium, palladium, expensive and rare. So that's potential downside. Methanol is also toxic and needs to be safely contained. So if humans interact with it, drink it, breathe it, it's not that healthy. So that's a downside as well compared to hydrogen gas or the waste product of water from the hydrogen fuel cell. Not much to worry about in terms of toxicity. Okay, what else? So here's a graph that really shows the difference in energy density, energy per unit volume between the lithium-ion battery compared with the methanol fuel cell. So we're not comparing with hydrogen here, but we can get the point across that the methanol fuel cell is very efficient when it comes to density. So if you need a lot of energy, fuel energy in a small space, methanol is the way to go. It's even better than the lithium-ion batteries that are in our phones and computers for most of the cases here. And I think this is even more obvious when you compare the density between the methanol fuel cell and the hydrogen fuel cell. Methanol is far superior. So practice 3 here. What's the advantages of a hydrogen fuel cell over the traditional lead acid battery? I'm gonna go type this again. Okay, advantages of the hydrogen fuel cell. There's absolutely no toxic materials in the hydrogen fuel cell, whereas the lead acid battery contains lead, very toxic to humans, and acid, which although is maybe not extremely toxic, it is like corrosive. And what else? Easy disposal. Once the battery is dead, the lead acid battery, you have to throw it away somewhere and do it carefully. Whereas the hydrogen fuel cell doesn't really contain toxic materials, just a couple electrodes and catalysts and structure of the cell itself. What else? No charging time. You know, if you really need to go now and start your car, if your battery's dead, you need to charge it, essentially. Whereas fuel cells, you just put the fuel in and it's always ready to go. No decreased performance based on charge. So when batteries get low, they often lose voltage as well. So they kind of get worse energy output as they discharge and get lower amount of energy stored, whereas the fuel cell, it kind of has a constant amount of energy output. B, then explain the feature of the hydrogen fuel cell that allows the passage of ions between electrodes. So the proton exchange membrane. Okay, the proton exchange membrane allows specific diffusion of protons while excluding any other ions, molecules, and electrons. This allows a complete electrical circuit, prevents the buildup of charge. So those of you in physics might know this, or if you've already studied electrochemical cells in chemistry, but if we get too much charge building up in one spot, like too much anions or too much cations, that's an unstable kind of thing to happen, a lot of charge in a small space, and it will eventually stop our chemical reactions from proceeding. It pushes the equilibrium backwards and stops things. So we have to prevent the buildup of charge. The exchange membrane allows, when protons start to build up, travel to the other section of the cell. All right, that's important. And it prevents chemical combustion of the fuel. If we allow the hydrogen and oxygen atoms to meet, and oxygen molecules to meet, there's a chance they'll just combust and release all their energy exothermically, and we can't control it. So that's why we need the proton exchange membrane. Okay, that's good. I'm just gonna move this up. Okay, C is deduce the half equations involved in the direct methanol fuel cell. I'll write those with my pen in a second. Let's consider number 2 though. Outline one advantage and disadvantage of the DMFC compared to a hydrogen fuel cell. So advantage, let's say higher energy density, much higher. Energy per volume of fuel, often important. Minimal explosive risk of fuel. If we're putting hydrogen gas into the hydrogen fuel cell, we have to be aware that it's very reactive and explosive. Methanol, not much to worry about. It's slightly flammable, but other than that, it's much more stable. For disadvantage, what can we say? So methanol is toxic to humans, causing organ failure and blindness and sickness, many things. What else? Lower energy output per mole. And there are other things like it releases CO2. So, we'd rather photosynthesis maybe just remove CO2 from the atmosphere, but we are going to combust it here when we combust the methanol. So we'll put it back in the atmosphere. I think that's fine. Okay, so then we'll answer C1. The half equations. I'd recommend you memorize these if you can. So we have methanol reacting with water. To make CO2 gas, 6H plus and 6E. That is the oxidation reaction, part of the full equation. Reduction then. This will involve O2, so 3/2 parts O2, along with 6H plus when it comes through the proton exchange membrane. And 6E, we can make water, 3H2O. Okay, so you can try to memorize these or deduce it yourself. I think the hardest thing is to realize methanol is reacting with water and not with oxygen or some other thing. If you can remember that though, you can piece together that this will produce CO2 and H plus, and then oxygen just sort of takes the parts of water that it requires, electrons and H plus, to make H2O. All right, that should be enough. So finally, just a table here that shows sort of the difference in energy density, energy per unit volume, versus specific energy, energy per kilogram, mass units. These are wildly different, and you might have concerns over one more than the other, depending on your applications. So for example, compressed hydrogen, even compressed, it has a terrible energy density, 1.9 megajoule per decimeter cubed. Hydrogen just takes up a lot of space to get a certain amount of energy, right? 1.9 megajoule per decimeter cubed. Compare that to its specific energy, though. If you're worried about mass, like maybe you're trying to launch a rocket, you need as little weight as possible to escape the Earth's gravity. In that case, you're really concerned about specific energy, and hydrogen basically can't be beat. Per kilogram, it has the most potential energy output, 120 megajoule per kilogram. But then if we look at the liquid fuels, methanol, liquefied natural gas, liquefied propane, gasoline, sort of the organic liquids, there's some differences between their energy density and specific energy, but honestly, most of these specific energies are fairly similar. Energy density things like gasoline certainly have the highest, but there's not that big of a difference between them. But these little differences can make a big difference depending on how much you're trying to min-max or get the absolute best fuel for your situation. And I think that's all I have to say. Yeah, so we're at the end of the fuel section. It's a bit weird. It combines many different topics, but our question was, what's the challenges of using chemical energy to address our energy needs? We've seen a lot of challenges. You have to consider what's the energy output. Is it easily accessible, combustible, or can we make a fuel cell with it? What about transportation and storage? Is it safe or stable? What about the economics of producing it? What about the greenhouse gas emissions, the effects on the climate? Hundreds of things to consider. They're all challenges, okay? But you just have to probably list a few if you're asked on a test. All right, hopefully you enjoyed. Hopefully you learned something. Next time we will get into Reactivity 2, I believe. We'll get into stoichiometry, balancing chemical equations, limiting reagents, those kind of things. All right, that's all. See you next time. Bye-bye.